Good morning, good afternoon, good evening, wherever you may be. We're going to kick off the first of the webinars for VROC. We try to do these every quarter, and we're fortunate today that we have a topic which is very current about the new energy ecosystem and how our AI offering is able to work in that environment. Trevor Block, who's our CEO and CTO, will be presenting, and I will be moderating the questions at the end of the session. So please feel free to put your questions into the chat box, and I will collect them and make sure that all of your questions are answered. And if something is left over, then we'll make sure we get back to you straight away after that. So a quick introduction, VROC is based in Perth, Western Australia. We have a global footprint with distributors and partners, and we have clients all over the world at the moment. So what we offer is something quite unique, and I don't want to steal Trevor's thunder by telling you about it, but we'll be talking about our low-code, no-code AI and how cost-effective it is in pretty much every scenario, but typically how it's able to work in the new energy world. A quick introduction to Trevor. Trevor started the company about 7 years ago and has been instrumental in developing all of the systems and processes that form the VROC platform, which is now broken up into 4 distinct offerings, which we are happy to talk to you about at a future date. Trevor comes from an industrial engineering background and spent a lot of time in instrument control systems till he moved over to the AI world and developed this unique offering for industrial data. So with that, I'm going to hand over to Trevor and let him take you through the presentation.
Great. Thank you, Arvind. So just to add on from what Arvind has been saying, I guess I'd like to personally welcome you to this webinar on AI for the new energy industry, and how the use of no-code or low-code AI is enabling operators and owners to produce valuable insights faster and easier than ever before. So I'll just start the presentation. There we go. Excellent. So I guess to get started, this diagram is a simplified diagram of part of the new energy industry. I guess there's lots of talk, lots of initiatives, and lots of money being invested into diversifying energy production. We can see the current shift away from gas in Europe, the huge proliferation of rooftop solar in Australia, and the huge amount of investment currently pouring into hydrogen and battery technology globally. So some of these initiatives are obviously involved bringing in new sources of energy, while others are just making the existing sources of energy more efficient. However, what we can see from this diagram is that many of the new sources of energy are not continuous. So we've got onshore and offshore wind, we've got tidal power, we've got solar power, and even hydroelectric to some extent. So these all rely on external factors that are somewhat out of our control, like weather. So they don't have a guaranteed production rate. And so being able to manage the grid now offers a whole new set of challenges, and as well as opportunities, I guess. And that's what AI is really well suited to. So there are many areas that need to be managed on these new grids. So we've got the overall grid management. We've got ensuring that there's sufficient power available when it's needed. We've got optimizing maintenance and production from a plant perspective, but also from an individual component perspective. And we've also got optimizing the actual production of energy and the return that operators get from supplying power into the grid. So I guess this webinar is being driven by discussions that we've been having over the past few months. Some people want to be able to do all of this with AI. Some want to be able to only do parts of it. But they all are looking for a solution that uses no or low code, artificial intelligence to quickly and very effectively deliver insights and optimizations at a very low price points. And I guess if we look at all these different sources of diversified energy in the new energy industry, we can see that although they are quite different, we've got wind, we've got solar, we've got conventional gas production, the one thing that they do have in common is that they all produce lots of data. And because they all produce lots of data, that's the perfect, AI is the perfect solution to use to process that data and to provide the insights that are going to optimize and really drive this new energy industry. And so with data being the common connection, just how much data are we producing here? And this is just an example of how much data we're producing for the different types of energy production assets or generation assets. So you can see wind turbines, which we're looking at 500 data points every 10 minutes, and a lot of wind turbines produce a lot more data than that. We have offshore production platforms, and obviously these platforms provide the gas to power some of the gas-fired power stations. And so these have 30,000 to 250,000 sensors on average and can generate a few terabytes of data a day. We've got utility power stations with 1.1 billion data points a day. And one of the gas service providers that we deal with at the moment, they've got hundreds and hundreds of gas compressor stations in their network. And so obviously each gas compressor station is producing lots of data, and being able to manage a huge network like that is very difficult. And so using all that data and using artificial intelligence to process it is a natural fit for this organization. And some of the insights that these organizations are trying to generate from this data are shown here. So things like predictive analytics and forecasting. So forecasting future power production, how much power is going to be consumed by the network, how much power do we need to inject into the network to keep it to satisfy the demand. So predictive analytics and forecasting, advanced analytics, and that can include trying to optimize our production for times of day or times of the week when the power cost is high. So in markets where the energy price is floating, we can pick and choose when we inject the most of our energy into the network to try and get the highest ROI from the power that we're producing. For network operators, we've got energy management. We've also got alert systems to identify when things are going off the rails. We've got real-time grid monitoring, so we can understand where the consumption and the production around our grid is happening and where the weaknesses or the risks might be emanating from. And we've got predictive maintenance, which allows us to plan our maintenance ahead of schedule, perform maintenance when it's the most opportune time for us to ensure that it costs us the least amount of money and that we ensure that we maintain the highest amount of reliability for our assets. And of course, maps view is very important in these sort of industries because we want to see geographically where our assets are and where's the production, where's our revenue coming from. We might have wind farms, we might have solar, we might have offshore production platforms. Where are they located and how are they performing in real time? So these are some of the critical insights that a lot of operations are looking for at the moment. And of course, all of this needs to be provided in real time. So we know exactly what's happening right now. And as things change, we can be informed immediately as to what's changing and how it's changing for us. And so to produce these, traditionally, this was a very laborious process. So it involved a lot of modeling, a lot of statistical mathematics, a lot of subject matter experts and data scientists coming in and building models for each one of these things that we need to do. So providing a solution for predictive maintenance, providing a solution for real-time grid monitoring, providing a solution for advanced analytics. These were all separate activities that were performed by experts over periods of time to slowly build up a portfolio to enable the smarter operations. But now with the advent of low-code or no-code solutions, we can now produce these same insights much more quickly and with a much lower number of people than we needed previously. And so that's the whole idea of this no-code AI, is producing these really detailed insights that allow operators and owners to optimize their assets, but without the huge upfront cost of having data science or subject matter experts spending a lot of time producing these artificial intelligence models. And so the way that no-code or low-code AI works is that we take historical data. So ideally, we take a number of years of historical data. 1 to 2 years is perfect, so we can see the changes in the different seasons and different times of the year. But it works equally as well with just a few weeks or a few months of data. We take historical data and we couple that with live data. And the live data is very important because as things change or as you make changes to your network or to your assets, you want to see what effect those changes have in real time. So by injecting live data, as things change or as you make changes to your assets, we can see the effect those changes have had in real time. And so we take the historical data and the live data and we feed that into a machine learning model, or a machine learning engine, I should say. And the machine learning engine takes all that data from all our assets and tries to find out how they all work. What are the connections between all those assets? What constitutes good operation? What constitutes bad operation? How does this thing work under all different operating conditions? And not only does it look at your assets as a whole, so if you've got wind farms and solar and gas production and offshore production platforms, it can look at this as a whole. We can look at it we can look at individual components as well. So you can look at individual wind turbines, you can look at individual bearings, you can look at individual solar panels, we can look at individual pumps or compressors on offshore production platforms. We can look at those individual components and we can look at the individual assets. So you can look at the whole wind farm or the whole solar farm or the whole production platform. And you can look at it as a system. So we can look at the whole network, how these things relate to each other and how they're interconnected. And that's the beauty about using machine learning. We don't have to tell the system how these things work or how they're connected. The machine learning AI engine can look at the data, and from the data alone, it can work out what these complex interconnections are and relationships are between all these different components in your system, or all the different assets, and how they perform together to produce whatever outcome it is you want to produce. And so for this, we can look at not just the equipment and the generation capacity, we can look at the supply and the demand and the transmission and the distribution. We can look at this whole network together to understand how this whole thing works under all different operating conditions. And so the AI system may build tens or hundreds or even thousands of AI models for each different component to understand, how all these things work in relation to everything else. And so once we've got these models built that determine how things work together, we can then start using these models to provide some insights. We can do things like predicting future production. So we can identify what's the demand going to be like in future and what's our supply capability going to be in future. We can look at minute degradation. So when there's minute changes to the way things are operating, we can spot those ahead of time or very early on and start taking the appropriate action. If there's future failures that are identified, the AI can see the leading indicators that might point towards a future failure, so we can take some preventative action and prevent the failure from occurring in the first place. For detailed root cause analysis, if we've had a specific incident and we're not sure exactly what caused it, we can run some AI models to try and work out, what was the sequence of events and what was the thing that caused the root cause for this particular incident that occurred. Identifying opportunities for optimization. So how can we optimize our production or improve our ROI, reduce our consumption or reduce our CO2, and identify risks and priorities. And these are some common insights that people are interested to find out about their assets. And so once we've produced all these insights, the idea with no-code or low-code AI is that all your subject matter experts and people that are interested in finding insights can build AI models themselves. So they don't need to know anything about data science or artificial intelligence. They can simply go onto a low-code or no-code platform like this, and they can build models for whatever's interesting to themselves. So if they want to know when something's going to fail, they want to optimize the production, whatever the thing that they want to do, they can go on and through a wizard interface, they can tell the system what they want to learn or want to know, and the system will automatically build these AI models for them to look at a specific problem that they're interested in. And if it's a problem that is continuous, so if you want to, for example, predict or forecast your power production, as new data comes in, this model will automatically update in real time and provide you updated insights. If it's a one-off model, say you want to find the root cause of a particular failure that you had, then you can do that model and you, within a very short period of time, get the answers to identify what the root cause was. And very quickly, what you find is that because all these subject matter experts are building their own AI models, looking at all the critical parts of all your infrastructure towards your wind turbines, your solar, your power generation, your transmission distribution, whatever it is, you end up with a really fantastic set of models that are identifying all the critical points of the assets that you run. And so because you end up with, potentially thousands and thousands of AI models, we need some way to aggregate them together to make sense of all of them. We don't want to go through looking at 1,000 models to work out if our assets are healthy. We want a very clean, easy to use dashboard to identify how all our assets are performing. And so this slide here is an example of an aggregated dashboard that's automatically produced by this system. So we can see each square represents a different part of your network. So we've got transmission, we've got distribution, we've got residential consumption, industrial consumption, and then we've got our generation. So we've got solar energy, wind, tidal, gas, hydro, and hydrogen energy production. And so what each one of these squares represents is that all of the AI models that are looking at each one of these components are saying whether that area is healthy or not. So we can see transmission and distribution are both shown as warning, which means that one or more of the AI models in that area are showing that there's something that we need to be concerned about. Whereas if we look at our solar energy and our wind energy network, they're all okay. So all the AI models in those areas, which might be thousands and thousands of them, are saying that we can't see any issues in this particular area. And so the idea with this dashboard is that you can very quickly and easily, it's very simple obviously, but you can very quickly and easily get a really good idea of where you need to focus your time. So obviously we need to look at our transmission and distribution networks and our tidal energy network. Those are the three areas that the AI is saying there's some problems with that we need to attend to. All these other green squares basically mean we don't need to do anything because the AI models, or the thousands of AI models that are looking at those areas, are saying everything's fine. Okay, so now that we know there's specific areas we need to look at, what we can then do is we can drill down into these areas. And I won't go through this in too much detail, but we can see that the idea is that if we look at, say, our tidal network, which has a problem, we can drill down, we can get a DNA map, which is the middle graphic here, and we can get a detailed root cause analysis of what's going on in that area, right down to the sensor level. So the idea is that we know there's a problem in that tidal network. We can drill down and find out exactly what the AI thinks is the problem, where the problem is, what's driving the problem, what the root cause of the problem is. And so your engineers or subject matter experts have all the information at their fingertips to be able to very quickly and effectively solve that problem and overcome the issue that they're having. Again, because all this is in real time, once they make the changes required or they repair the piece of equipment that's faulty, as the new data comes into the system, all the AI models automatically update, and that red square that we saw on the overview page, that will go green, indicating now the problem is fixed. So not only can this tool be used as identifying potential failures or degradation of equipment, once you've performed the repairs and made the changes, we can then go back and use this to validate that the repairs have been performed correctly and that the equipment is now operating the way we'd expect it to operate. And that's the idea of the system, is to give you all the information you need to understand how your assets are performing, being able to drill down to specific problems and identify what needs to be done. And once you perform the work and optimize the system or repaired the piece of equipment, we can get the real-time data to show you that it's all working properly again and that the repairs you've performed have been successful and effective. So that's the idea of these systems. So that's a kind of very, very high-level view of how no-code, low-code works. What I'd like to do now is go through some specific case studies just to show you how it works in practice in the new energy industry. And at the end, we'll go through and do a bit of a wrap up on how this technology works and how the deployment of this technology works in practice. Okay, so this use case is for wind energy. And so for this one, we had a customer who has a wind farm. They've got a number of wind turbines. And the wind turbines that they have switch between star and delta mode of operation at various wind speeds. So at some wind speeds, they're in one configuration. And when the wind speed gets above a certain amount or some certain speed, these turbines then change operation into another mode of operation. And the reason they do this is to try and get the most energy out of the wind. They want to try and return the most energy or produce the most energy they can for the current wind speed. And so the benefit of star-delta switching is obviously you try and optimize the energy production. But the disadvantage of star-delta configuration is that each time you switch, that's obviously an operation that can cause a fault. So anything that changes between star and delta can be a maintenance issue because it can increase the chance that something fails by the very fact that you're switching from one mode to another. And so the idea with this study was to really identify the benefits. Do the benefits of switching between star and delta overcome the additional maintenance cost and the reduction in reliability that you might get by switching each time? And so what we did in this case is we took a year's worth of historical data to understand how this wind farm operated over the different seasons of 1 year. And we used artificial intelligence to try and identify how the thing should perform the successive year. And some of these turbines were fixed in star or delta mode, and some of them were allowed to switch between star and delta. And so what we did was the AI allowed us to compare under the same wind direction and wind speed, how would a wind turbine, how much energy would a wind turbine produce if it was allowed to switch between star and delta configurations, and how much would it produce if it wasn't allowed to switch between star and delta configurations. And so that difference enabled us to identify how much additional energy we could produce by switching between star and delta and what the value of that energy was. Similarly, the system could identify, the reliability of the turbines as well. So what was the decrease in reliability or the increase in maintenance required for turbines that needed to switch between star and delta versus those that didn't? And so in this particular instance, what we found was that there was very minimal improvement in, or very, very minimal increase in energy production by switching between star and delta, just by very virtue of the fact of the wind speed and direction of that particular area. So although the turbines were switching between the two modes, there was very little real energy or additional real energy being produced because of the switching, compared to the cost of the additional maintenance and the reduction in reliability caused by the switching. So in this case, there was no point in switching between star and delta because the returns didn't outweigh the additional cost of maintenance. One of the things we did find that was interesting on this case is that when we compared year on year the wind turbines, we actually found that one wind turbine was performing significantly worse year on year than it was the previous year. So under the same wind speed and the same wind direction, the same wind turbine was performing between 30 and 50% worse than it was the previous year. And so this is something that the operator of the wind farm hadn't picked up themselves. This is something that was only picked up as a byproduct of this activity, because that's what the artificial intelligence noticed, that under the same wind conditions and the same wind direction, one of the wind turbines was performing significantly less. And so that was a case where the operator could be notified of this, and they could perform repairs or inspect that turbine to identify why we were getting the significant reduction in power production and make the required repairs to improve that. And the savings from that were much bigger than any savings that they'd been able to achieve through the star delta switching. So by looking at all the data and in a totally unbiased way, we're able to find insights that we weren't even looking for, because that's the way the AI works. It's just comparing year on year how these facilities perform and identifying where the potential opportunities are for optimization or improvement. Gas grids is another one that we've had quite a lot of experience with this sort of technology. So we have a client with hundreds of gas compressor stations around a gas network. And so obviously with hundreds of gas compressor stations, it's very difficult to spend a lot of time investigating each individual compressor to make sure that it's operating reliably and optimally. And so what this client had was they had one gas compressor that was failing on a regular basis. So every few days, one of their gas compressors in their network was failing, which required them to go out and reset it and restart the gas compressor. And they'd spend a lot of time with their subject matter experts and their OEMs trying to identify what was causing the failures. And after a number of years of investigating this gas compressor, they still had no idea what was causing it or how to prevent these unplanned failures. So they pushed the data, they pushed a number of months of data into this low-code, no-code AI system, and they tried to do a root cause analysis to identify, what was causing this compressor to continually fail. And so within 10 minutes, the system had produced an AI model and it produced a root cause analysis of what was driving these particular failures. And so what the client did was during their next shutdown, they performed all those 22 items, or they rectified all those 22 items that were identified. And when they restarted the gas compressor after the maintenance period, they found that the gas compressor ran for 4 months continuously, which was the longest it had ever run since it had been installed. And the only reason they shut it down was for some other operational reason. So in 10 minutes of AI modeling using one of these solutions, they were able to solve a problem that they hadn't been able to solve in over 2 years. And the clients indicated that the increase in uptime saved their business around almost $22 million US. So that's a case where using a different technique, using an unbiased AI model, can provide really significant results in a very short period of time. I'll just go on to this one very quickly. So network forecasting is quite important, especially for countries like Australia, where there's a large amount of rooftop solar. So in Australia, there's 25 to 30% of houses and businesses have rooftop solar, which obviously produces a significant amount of energy into the network. This energy is quite volatile because obviously it's based on the weather. When it's sunny and there's a lot of solar being produced, the network performs a lot differently to when it's cloudy or overcast. And so being able to forecast the demand of the network in advance is very important to ensure that there's enough spare generation capacity to cover any shortfall in the solar production. And so this engagement was to see whether one of these no-code or low-code AI systems could forecast energy demand 72 hours in advance. And so what VROC did was we ingested 2 years of historical substation data from all the substations around this network. And what we found is that we were able to provide a forecast, an hour-by-hour forecast, 7 days ahead, with a mean error rate of 5.5%, which was much better than the network operator had been able to achieve previously. So for every hour from the current time to 7 days ahead, the system was able to provide a forecast of what the expected energy consumption would be within a 5.5% error rate. And so what this allowed the operator to do was to ensure that they had just enough generation capacity to cover the shortfall and meet the demand of the network at all times. Whereas previously there were times where they had insufficient generation capacity, which obviously wasn't a good outcome. But in a lot of cases, what they did was they erred on the side of caution and they had excessive generation capacity, which although kept the network stable, was obviously not a very efficient way to run the system. And so being able to have a highly accurate forecast 7 days ahead allowed them to tune the generation capacity to ensure the network was always supplied with the right amount of energy at all times. The final use case I'd like to go through is ESG reporting and KPIs. So for a lot of energy production companies, so VROC are working with quite a few of them at the moment, they have very diversified portfolios. So they've got offshore oil and gas, they might have onshore oil and gas, they're now getting into wind, they've got solar, they've got a lot of different, and possibly even hydrogen as well now. There's a lot of different energy production facilities that they have around the world, and trying to understand how they all work together and what the benefits and drawbacks for each one of them are is very difficult. But the great thing about this technology is that you can actually ingest data from all of these facilities simultaneously. They all have data, so you can easily compare an offshore oil and gas platform with a wind farm, with a solar farm, and you can get very good ESG reporting and KPIs on how much energy they're producing, what the ROI is, any maintenance that's required to be performed, what the benefit of performing that maintenance is, how much carbon you're producing or avoiding. There's a whole lot of KPIs that you can produce across a whole network of very, very different asset types. And that's the beauty about using this sort of AI, is that you can ingest the data and then you can compare things that are seemingly very different using standard KPIs and metrics and identifying where the most beneficial improvements can be made are. So if we were looking at improving our maintenance, if we're looking at improving our CO2, if we're looking at improving, any KPIs that we're interested in, we can use dollars if we want. We can see what we can do across all of these assets that's going to have the biggest return on our investment. Where do we focus our time? Where do we focus our energy to ensure that we meet our KPIs and we get the biggest ROI that's possible? And so using artificial intelligence and this no-code, low-code AI, we're able to do that very quickly and easily without having to spend a lot of time and effort building AI models and modeling the stuff manually. We can use AI to automatically model this and automatically, automatically compare the different types of assets that we have across our network. Again, if there are any interrelationships between our networks, so between our solar or wind or offshore production facilities, we can see those very clearly as well through this technology. And if there's opportunities to optimize, the time that we're producing energy to take advantage of high energy prices, we can do all that across all our asset base. So it's an extremely powerful tool for organizations that have very dispersed and disparate asset types across different geographical areas. And so I guess to sum up, what we're seeing now is that low-code, no-code AI is able to provide meaningful savings. So as Arvind mentioned earlier on in this presentation, we've been doing this for 7 years now. And so we have some really good metrics on how much clients are saving by using this technology. It's no longer a something that needs to be proven. The technology has been proven time and time again. And a lot of our clients now are providing us the real ROIs and metrics of how much they've actually saved using this technology. So, millions saved by customers. The fantastic thing about low code, no code is there's no CapEx investment. So we don't have to install any sensors. We don't have to install any equipment. There's no big upfront consulting costs that's required. You basically send in the data and you can start achieving or receiving the insights almost immediately. On top of the AI, there's obviously regulatory compliance and OpEx reduction. That's just part of the solution with no extra cost. What we've also seen is that accurate predictions have led to rapid ROI. So in some cases, we've seen an 83% reduction in losses. We've seen asset reliability improve from 70 to almost 100%. We've seen environmental compliance improve from 50 to 100% in some instances. And obviously failure mitigation and avoidance has improved significantly by having this information available about how our asset base is performing and is likely to perform in future. The implementation time of these things is extremely fast. So we have your implementation in less than 4 weeks. Most of that 4 weeks is actually just getting access to the data from the client. The implementation really only takes a few days once the data is available and ingested into the platform. Once that happens, AI models to find insights or to do root cause analysis or to do forecasting, they can be trained in minutes by any personnel. They don't have to be familiar with AI or data science. And the system can produce real-time alerts and predictions up to 8 weeks in advance. So you can very rapidly be up and running with this technology without any, upfront cost or any additional hardware requirements. So I guess for operators in these new diversified energy markets, being able to quickly make decisions in real time with all the information at their fingertips is important to optimizing their operations. And using low-code, no-code systems such as VROC allows them to get the best production out of their assets at the right time to maximize their ROI and reduce any unnecessary costs. As I mentioned, the main benefit for this technology is it allows it to be rolled out and put into production faster, easier, and more cost-effectively than ever before. So you can start receiving insights and improving your ROI in a very short period of time. So I think that's probably where I'd like to leave it today. Thank you for your time. I hope this presentation has given you an idea of how these AI systems can be used in production or in practice. And I think now we're happy to answer any questions that you may have about this technology or how it's applicable to your particular industry.
Thanks, Trevor. Let me start off with some of the more specific questions that are in the chat box. On your slide with the gas grids, you talked about a particular case study with a gas compressor. Can you give us a little bit of the history of that and exactly what happened?
For the gas compressor? Yeah, sure. So the gas compressor case study.
This is the Dulang one.
Yeah. So this gas compressor, again, it's a gas compressor where the client had it installed. It had been very much a troublesome asset for them since the very beginning. They had a number of subject matter expert teams that they put together that spent thousands of hours trying to work out what was causing these regular shutdowns they were having on the compressor. They had the OEMs come out and have a look at the compressor. So obviously they looked at the compressor and they looked at all the systems around it as well, the separate OEMs. But all of the OEMs suggested that their particular components were working fine and it must be a problem somewhere else. And so the client provided a few months worth of historical data showing a few failures that had occurred on the compressor. And what the AI was able to do, I guess, was to not just look at the individual components of that compressor. It was able to look at that whole system as a system, I guess, as an interconnected system, and to identify where the problems were. Because obviously it wasn't a specific problem on one part of the system. It was more systemic problems across the way that the compressor was being operated. I mean, some of the items that were picked up were obviously related to individual components. So for example, one of the operating modes was left in manual mode rather than auto mode, which is a pretty basic a mistake, and it had been that way for months. But other things that were picked up were more, I guess, difficult to identify because they relied on a number of complex interactions between different components within the compressor.
And also, can you comment why they chose VROC to do this, considering they had a huge range of experts to look at it?
Well, to be honest, I think they said they were desperate, weren't they? They had no other options. They had tried all of the traditional options to try and solve this problem. So they had tried as I said, their subject matter experts, their OEMs. They wanted to find a company that knew nothing about compressors but could process that data for them, and use that data to try and deliver a solution to the problem. So they wanted a company that wasn't an expert in compressors, but was an expert in processing industrial data, so that they could let the data tell them what the problem was. So it was a very forward-thinking individual that decided to go this way, but in the end, it proved to be the right way because they solved the problem.
So I have another question from an attendee that's part of the chemical industry. So that would be one of the clients taking the power and the gas for the utilities. And their question is more going back to what you mentioned about the data. So the data seems to be key to all of this. How do you, if a client already has DCS or a historian, how do you get the data onto the VROC platform, and then what happens to it after that?
Yeah, sure. So the VROC platform, so there are a number of deployment, I guess, ways we can deploy the VROC platform. So it can be deployed, obviously VROC have their own private data clouds where we can store your data or store clients' data. The platform can also be installed if a client has AWS or Azure, we can install the software into their own instance so that they've got full control of their data. Or if they want to just install the system on their own local data centers, on servers within their own data center, we can do that as well. So there are a couple of deployment methods depending on any data sovereignty requirements that the client may have. And obviously, depending on which deployment method we go for, will determine how we get access to the data. But generally, for most historians, we will have either have the historian export data on a regular basis, every few minutes or something like that. Or if there's a connector available, we will connect to the historian directly and pull the data on a regular basis. As I said, usually what we try and do is we try and export 1 to 2 years of historical data if that's available, and then set up the real-time streaming. Now, of course, real-time streaming doesn't have to be real-time. So it can be near real-time as well. So we can pull data every 10 minutes. You can pull data every hour. You can pull data once a day, depending on the communications link that's available. Obviously, the AI models and the insights will only update when new data arrives into the system. So depending on how frequently you want the models to update and the insights to update, that will determine how often we pull data. But VROC as a company, we've got experience connecting to the majority of historians and DCS and PLC systems. So I don't know which one they have specifically, but I'm sure we've more than likely connected to it in the past.
All right. So it doesn't really matter which industry it is, as long as the data is available to be streamed in some form.
That's right. As long as some historical data is available, and there's some real-time data that we can get access to, that's all we need.
All right. I just want to take you to one of your slides. I think it was slide 11, where you talk about the use case of ESG reporting and KPIs. So that's becoming very popular. But one of the things you talked about is being able to look at the whole system. Yes, this one. Being able to look at the whole system and then allow the customer to decide where they need to spend their money to get the best outcomes depending on what their KPIs are or what they want to achieve. So, for example, lowering carbon emissions versus improving process efficiency. Can you just comment about how that works on a holistic space? Because it really is very similar to the second slide where you showed the whole ecosystem of the new energy.
Yeah, sure. So obviously for each individual plant, there's a whole lot of things that we can do to I guess, improve our ROI. We can obviously reduce our maintenance. We can improve our reliability. We can change some of the settings on the plant to make it work more effectively. We can reduce the potential resource usage of those facilities. There's a whole host of opportunities that we might have for each facility. And obviously by using AI, we can look at each facility individually very quickly and identify what those opportunities are. If we have financial information, we can then also, or other information, we can then put a cost against each one of those opportunities. So what's the ROI expected if we improve our reliability? What's the expected ROI if we reduce maintenance, or if we reduce our resource usage? We can automatically have the AI incorporate the financial metrics into any modeling that it's doing. And so what you end up with is you end up with I guess for each facility, you end up with a whole menu of options that you can do and what the expected ROI for each one of those options are. These sort of systems can then automatically aggregate those up, so we can see, how much benefit can we get from our wind farms or our solar farms or our offshore oil and gas platforms by optimizing them or improving their reliability or reducing the maintenance costs or reducing resource usage. And so we can look at our whole asset base through this lens and say, where do we want to spend our time? Do we want to spend our time on our wind farms, on our solar, or on our offshore oil and gas? Where are the benefits coming from? And of course, we don't just have to do that based on cost, based on dollars. We can, if we want to, we can just do financial analysis on that and say these are dollar ROIs. But we can do that based on other KPIs, as you mentioned, Arvind, such as production rates. We can do it based on CO2. We can do it based on any other KPIs we can even do it based on health and safety. What's the health and safety risk or the environment risk if we don't perform this maintenance or don't do something or other? So being able to look at it through these different lenses allows us to make much better decisions and see what the trade-offs are. So if we want to do whatever is going to give us the best financial outcome, that may not be giving us the best environmental outcome. So understanding what these relationships are and how these things are related allows us to decide, where we want to be and what the best course of action is at that point in time.
All right, great. So one of the questions we get quite a lot is about specific pieces of equipment and what our experience has been at that. And in this case, the question is about a specific gas turbine made by GE. So how does our system cope with different companies' equipment? And is any specific expertise needed to be able to I would say, build models for different types of equipment?
I guess this is where this sort of low-code, no-code system that we use is a bit different to a lot of other systems in that it doesn't use pre-built or pre-canned models for pieces of equipment. So we don't need a model for a GE compressor model XYZ to be able to understand how that piece of equipment is performing. The idea with these systems is that we look at each piece of equipment individually. So we look at each individual compressor individually because they all operate slightly differently. And so when these sort of systems are modeling individual pieces of equipment, they don't model the pieces of equipment in isolation. So we don't look at that individual compressor by itself. We look at how that compressor operates in connection with everything else around it. So how does it operate when things upstream change, when things downstream change, when the conditions surrounding that piece of equipment change? How does that specific piece of equipment respond? And so by doing that, we can understand what good operation looks like, what not so good operation looks like, and what a potential failure situation looks like. So for these pieces of equipment, we don't need to have a pre-canned model for that exact piece of equipment. We just need some historical data that allows the AI to learn how that equipment normally works under different operating conditions. And so the person driving the solution doesn't really need to know how that piece of equipment works. They can build a model at any level they want. So we've got a gas compressor. We know what the gas compressor has to do. We've got a few outputs from our gas compressor. As long as it's doing that, we think the gas compressor is fine. So we can build a model, say, whenever the gas compressor isn't doing what it's supposed to do, then we need to be notified beforehand and identify what's driving that particular undesirable outcome. So these models can be built at any level. If you've got a a gas production facility, maybe all you care about is that we're producing gas of the correct spec at the outlet of the facility, and that can be our model. AI, build me a model that's going to tell me whenever my facility isn't producing gas at this rate and with these parameters, within these parameters. And that will then look over your whole facility and tell you whenever it thinks that one of your parameters are going to go out of spec or your production rate is going to be too low. So you don't really need to know too much about each individual piece of equipment to build the models. You just need to know what outcome is that you're trying to achieve by your facility. Where you will need subject matter expertise, obviously, is to perform any rectifications. So if the AI says, we've got a problem with this bearing, the bearing vibration doesn't look right or looks too high or the temperature's too hot, you'll need a subject matter expert to go there and work out how to change that bearing, obviously, and what that means. And if there's some other work that's being performed that might be driving that particular undesirable outcome. But to build the models, you just need to know what your equipment needs to do. You don't need to know anything else apart from that. The system will work it out itself from the data.
All right, I've got two questions that relate to this. The first one is, how is that different from existing systems that you can, download the data into Excel and then build your own, I would say, trending models? And the second part is what you started off with, this low code, no code. How does that work in this instance and translate into much better cost-effective solutions for customers?
Yeah, sure. So traditionally, a lot of this analytics, there's sort of two ways to do artificial intelligence with these sort of systems. The one is, as I mentioned, the pre-canned models, where you have a specific model for each piece of equipment. The other way, which obviously is not very accurate because each piece of equipment, depending on how it's been maintained and operated and where it's situated in your plant, will operate slightly differently. The other way is to do manual modeling, and that's kind of been the traditional way of solving these problems, over the past few years. Is you have a problem with a compressor or you want to monitor your compressor, you put together a multidisciplinary team of subject matter experts and data scientists, you get all the data and you set up a project to build a model for that particular piece of equipment. And that can take anywhere from, 3 months is probably a very quick one, but between 3 and 12 months is how much time it usually takes to build a model for something like that, to identify the health of a gas compressor. The idea of low code, no code is to, rather than doing that, rather than having your team of SMEs and data scientists build this model, which is obviously time consuming and quite expensive, we let the AI understand your data itself. So you tell the AI the type of model you want to build, and we have an automated system that goes away, processes all the data, tries to find out how that piece of equipment works automatically just by looking at the data. So obviously, if you're using servers to process this data and to try and build models, it's going to be a lot quicker and a lot more effective than using, humans to do it. So rather than using, a team of 10 humans, we use a team of, 200 servers to try and come up with the same outcome a lot quicker. What you'll find is that you may find that the automated system may be slightly less accurate than the human system by a few %, but the advantage is obviously that you get an answer within minutes rather than within months. And these AI models that are generated by low code, no code systems, they automatically update. So the life cycle of the model is automatically managed. So as things change or as your equipment is maintained, these AI models are automatically retrained and automatically updated in real time without any intervention required by the user to ensure they stay current. Where the previous method, you've got to go through that whole data science methodology again to update your model manually. So the cost and time savings are significant, and the accuracy of the models is very similar to what you'd get by doing it the traditional manual means.
Does that translate into much, I would say, much more cost-effective solutions for the customers?
Yeah, sure. So an engineer can produce, 20 or 50 models a day, whereas doing it the traditional way, you're doing one every 3 to 6 months. So it's a significant saving and allows you to roll out this technology a lot quicker and monitor more of your plant, getting a much better ROI for, much less cost.
All right. Let me move back to the original new energy scenario, because we've gone into industrial data. And what you find is there's many different participants. You've got the industrial users, then you've got the industrial producers, but not many producers are producing all of the different types of energy. So while we can take data from everyone and produce outcomes or insights for each individual stakeholder, it's very unlikely that in real life all of the stakeholders are in the same organization or company. So can you actually then be able to share data that is common versus data that is confidential if you had multiple stakeholders using the same system?
Yeah, I'm trying to think how that would work. I think it's definitely a possibility. Obviously, there is some information. If you're managing a distributed network, there is some information that you'll need from each of the generators and each of the consumers so that you can effectively model and understand what's going on with that system. And I think most of that information is probably already shared to be able to just manage the network even without using this sort of technology. But definitely, I mean, as I said, this technology is able to be deployed in various forms on different clients' systems. And obviously, there's different levels of access control that we provide. So either we can manage the access to data, or individual clients can have their own solution installed on their own operating environment that just looks at their data and shares just the limited amount of data required to I guess integrate it into the whole picture. But yeah, there's definitely technological solutions to do that, and ones that are already recognized and already being used by organizations around the world, I guess.
So one of the things you didn't mention is when we're doing predictive analytics, how far in advance can we predict compared to more traditional methods based on similar data?
Yeah, it's a good question. And this really depends on the type of problem that you're having. But for a lot of problems, I mean, the idea with predictive analytics is that we don't want to predict something just about when it's going to happen. So predictive analytics shouldn't be something where you need to send a notification to your phone to say this thing is going to fail in the next hour. The idea with predictive analytics is to give you time to understand what maintenance requirements are and to properly plan these things. So you want days or weeks or months notice before you have to do something. And so I guess that's the key is being able to have that time available to you before the failure so that you can properly plan and properly have the maintenance as a scheduled in a regular activity rather than as an emergency activity that you have to do. And so the time varies dramatically. So for some offshore oil and gas, I guess facilities, that previously for some of the failures they were getting, in the order of hours notice, so that there'd be, hours between thinking something was a problem to the piece of equipment failing. And so using predictive maintenance, you can get sort of 5 or 6 days notice. So significant improvement in the time and obviously, again, avoiding a shutdown. But it really depends, I guess, on the type of problem as to how much, notice we can get before the failure. You can be notified by predictive maintenance. It also depends on the failure type, I think. Some failures, something might instantaneously fail, in which case you're obviously not going to get much notice. But for things that have a degradation profile, days or weeks notice is not uncommon.
All right. So let's get back to the crux of new energy, which is, we've seen recently with a number of clients talking about hydrogen and how that fits into the fuel mix and things like that. So do we need to do anything special with our platform to be able to incorporate the new energy systems that are coming into play, or data is just data and then we'll be able to build models for hydrogen when electrolyzers or other new techniques come into play?
Yeah, as you mentioned, data is just data. So the beauty about these systems is they learn from the data. We don't have to, we can teach it if you want to, but the idea with these systems is that just by providing the historical data or the real-time data, over time these systems learn how the equipment operates or how the asset operates under different operating conditions, what's good operation, what's bad operation, what are the critical success factors that need to happen for this thing to perform successfully. And so over time, these things will learn how your hydrogen production facility works and how you can optimize it. Again, because it's building a huge mathematical model on how this whole system goes together, it's very easy to use that same model for optimizing, for the simulations, to say, if I change this parameter, what do I expect my plant to be doing? There's a whole host of things that you can do once the system understands how your process works under various operating conditions. So I guess to answer your question, no, there's nothing you have to do except feed data in, and the system will learn how your facility operates just automatically.
Okay, some more practical issues, which are, do our customers need to have knowledge of data science or data analytics to be able to use our system? Or do we provide some training for them to use our system? How does it work once we engage with customers?
Yeah, sure. So the whole idea of the system is to avoid people having to learn data science or artificial intelligence. So what people do need to know is they need to know the problem they want to solve. So, what is the thing I want to solve? I want to improve my production. I want to, reduce my downtime, improve my reliability. They do need to know what the problem is that they need to solve. But the idea with no code, low code is that you don't need to know anything about data science. You don't need to know anything about, artificial intelligence or machine learning. You just have to know what problem you're trying to solve, and the system will then automatically build models for you. So this is the whole idea of no code, low code. You don't need to know anything about AI. You just need to know about the problem you want to solve, and the system will do everything else for you. Obviously, once the model's built, it'll also give you a confidence and say, this thing that you're trying to predict, we can predict it with 95% confidence. So at least you know how accurate the model is that we're able to produce to solve that problem that you have.
Okay, now probably my last question is, if our customer already has data scientists, how can we help them do a better job with on our platform?
Yeah, that's a good question. So the idea with this platform is to solve the majority of problems very quickly and easily. So being an automated platform, we're not going to solve every problem. We might solve 90% of all your problems, and we'll do it very quickly. But there's always going to be a few problems that need to be solved by a data science team just because of the complexity of the problem. And so the idea with integrating this technology into a data science team is that this sort of technology can be used to solve 80 to 90% of the day-to-day problems extremely rapidly. Within minutes, you can have a solution to the problem that you're trying to solve. And so what this does is this frees up the data science team from having to solve these, I guess, in some ways, mundane problems, and allows them to focus on the more complex, high-value problems that these solutions can't offer. So what this allows you to do is to scale this technology extremely rapidly to solve 80 to 90% of your problems, kind of overnight. And then any other problems that can't be solved immediately, your data science team can then work on those to ensure that, we get solutions to these more complex, more difficult problems that can't be solved using automated AI.
All right, Trevor. Thanks a lot for that. I'm going to wrap up after this and just with a few notes. One is that I haven't asked one of the questions. So we had a question about the chemical industry. So I will respond to that specifically to the participant. Also on the questions about the gas compressor and turbine generator, we'll actually send you specific responses to those because we've seen the details that you want to see. But in general, what you'll find is on our website, a lot of the case studies are already available, and you're most welcome to register and download them. So most of the information is available, but specifically, we'll be getting back to you. We also recorded this and should have it available very soon for you to refer back to or to forward it to other people within your organization who may be interested in this. Thank you all for attending, and please feel free to send us any questions you might have, info@VROC.ai, and we will definitely get back to you on that. And on that note, thanks, Trevor. And also thanks to Megan, our marketing manager, who's been working in the background and to make this all possible. Thank you very much and goodbye.